Yeah, that's funny. Anyway. Yeah, that's a funny one. You can. It's kind of a wave. Like the last ones are not really jumping. Like. Yeah, we jumped together. And actually, I figured out. We should have. I should have been there, and you should have been there because then we would have closed the brackets. Uh, oh yeah, that should be enough. Should be enough. I will send them all to our CEO. All right, few organizational stuff, like one organizational stuff. Sadly, me and neither me nor Andreas can stay very long after when the conference is finished, which means after Sam's talk. And my other Andreas, my boss, actually just left the building right now. But some people ask us, what can we do to meet? So I named two guys to be the general beer managers. Guys, can you stand up? This is Niels and Greg. Yeah, that's so they know they know no they know they have to go to the to there. They know to have to go there. So you have to find that guy. This guy is probably Günther, and you will have an amazing. We should have sent them to the, what is it called? The place in Köln. And so yeah, hang around after the talk. At one point, Ollie, my boss, is gonna come and ask you to slowly but surely leave the building and join them and enjoy the evening. And I hope to see you guys, but I will come back once you're finished to say bye-bye anyways. The first time I saw Sam was at NS Conference. It's kind of a running loop. We always come back to NS Conference. And so since then we've been in touch, and when I asked him what he wanted to talk about, he said, do you want presentation number 1, number 2, number 3, or number 4? And we liked all 4 of them. That was a problem. If you could come up with a very shitty one the next time, that would make it easier for us to select. Oh yeah, I might, like in the middle of the talk, I would be like, yeah, do the other one. We really wanted to see something about concurrency, and I'm even more excited about concurrency since yesterday, because of the watch, because of all those monkeys in our watch. So, ladies and gentlemen, give Sam a big round of applause.
I don't think I'm muted. Can you hear me? Hello? I think I did unclick it. Hello, there we go. Now I realise it's like, I don't know what the time is, 20 to 4, and I see a couple of you with beers in your hands. If you'd like to take this moment to leave the room and grab a beer, I will not be offended at all, because this is concurrency. It's not the most exciting of subjects that we're going to go through. So if you feel like you could do with a beer to get through it, or at any point in the talk, if you feel like it's driving you up the wall and you really need a beer, do feel free to go and get them. In fact, there's beers being delivered if anybody needs a beer. There we go, we've got the first taker at the back of the room. So, concurrency on iOS. How many of you, before I even get started, are computer scientists or have done, I would say nobody's a computer scientist now because we live in the real world, but those of us that went to university and did some kind of computer science type degree. This is good news because I'm going to very, very quickly go through some problems with concurrency and what concurrency is, but not in great detail because I think everybody knows that. So a little bit of reminder, but no great detail. Then I'm going to talk about the different ways that you can do concurrency on iOS and in fact macOS, tvOS, watchOS and Linux, I guess now, and now that we can do stuff on the server. Using Apple's techniques, we'll talk a little bit about some of the slightly more advanced things that you can do. I'll do a bit of live coding so that we can see some stuff in action. And then right at the end, I'll talk about some of the non-Apple alternative concurrency models. So, to start out, I'm going to say that concurrency is hard. I think we all know this because I think we've all attempted to write things that then don't quite work. And the joy of writing bugs in concurrent programming is that you never ever see them in development. You see them in production. But then you can't recreate them because concurrent programming, the threading model, is stochastic in the way that the bugs appear, which is a pain in the arse. So what actually is it? As I said, I'm going to go really quickly through this kind of stuff. The idea of concurrency is very simple, that your device can do more than one thing at once. Even before we had multiple core chips, which all of the devices pretty much that we have now have multiple cores. Even before that, to us as developers who live in a world where 1 second seems like a short amount of time, then it appears to us that the system is doing more than one thing at once because it uses some kind of time-based multiplexing so that one processor will get a little bit of time on the processor and then another one. Now to us, that appears like two things are happening at the same time. Why do we want to use it? We want to use it to keep the things responsive, right? The way that the programming model works for building UIs and the such like is that you're only allowed to interact with the graphics processor pretty much, in most cases, using one thread. Now, if you then use that thread to go off to the network to request something that takes a really long time to arrive, then you're not updating the UI for your users, which becomes a sluggish, slow, and painful experience for people watching it. So we do things using concurrency so that the UI thread is always running and is always updating the UI to delight your users, which is apparently what a spinner is delighting users. Common concurrency problems, right? This is the bit that I'm going to go quite quickly through. I've got 3 examples of problems that you get in concurrency. Oh, I apologize. I've just done that thing that I hate that people in DubDub, when you watch DubDub videos, if they ever say a number, they hold their hand up with the number, as if we don't know what the number is. Like, I'm very privileged in that they speak in my mother tongue. But I imagine that you guys, the simplest words that they'll be using are the numbers 1 to 5. Out of all of the things that are going to be complicated and are maybe going to be difficult to understand if it's your second language, the numbers are not the things that are difficult. So it drives me up the wall when you see somebody walk across the stage. The 3 most important things. No, put a bit of life into it. Race conditions, right. So I've spoken about threads. We've got the idea of 2 things happening at once, and they happen on threads. Now, I'm not going to go into quite what threads are and how they work, because I think you probably know. I'm going to summarize what a race condition is. I've got a value that's stored in memory. This is something that you can only really access from one place at once. And I've got 2 threads. And thread 1 comes along and says, I want to increment the number that's in this value position. Oh, I could use this. Look at that. So, in order to increment that value, it first of all has to read it, because it needs to know, well, what's the number before I can increment it. So it reads a 1, and then it adds 1 to it, and then it'll write back 2. So 1 plus 1 is 2, so it writes that back to the memory. Then thread 2 comes along and says, I want to increment I want to increment the value as well. So it comes along and it reads a 2, it adds 1 to it, and then writes back a 3. Everything's great. We've come in 2 separate threads that want to increment the number 1 twice, and you've ended up with 3, which is correct. Now consider this position. Thread 1 comes along and says, I want to increment 1, so it reads 1. Thread 2 then comes and says, actually, I would also like to increment it. Now you can only do one thing at once. So thread 2 reads a value of 1 in. Thread 1 has had to stop because we can only cope with one thread at one time. It increments it to write back 2. Now thread 2 is finished, thread 1 comes back along, and it's already read a number 1, so it's just going to add 1 to it, incrementing it and write back 2. So now we started off with a value of 1, we've incremented it twice and got 2. Well, that's not really right. This describes in the simplest kind of form a race condition, where the ordering of the things that are happening makes a difference to the end result. This is incredibly difficult to recreate, because this kind of thing where which thread gets run at which time all depends on whatever else is going on in the system. Next one, priority inversion. This is another problem, and I like talking about this one because the example that I'm aware of priority inversion is based on the Mars Pathfinder mission in about 97, I think, where they had this problem. And if you think debugging on your iPhone is a pain in the arse using Xcode, try and debug something that's on Mars, because that's significantly more difficult from what I can understand. Right, so now you have this idea that threads or tasks have some kind of priority. I want to do the high priority tasks over the low priority ones. We've got some kind of resource, so we're thinking memory, or maybe it could be GPU, it could be network access or something like that. So a low priority thread comes along and it's all going along nicely. And then it asks for a lock on the resource. So I want this, nobody else can access it at this time. So it goes along all very happy. Medium priority task comes along. So then that stops the low priority, but the low priority still has a lock on the resource because it's still using it. Then a high priority one comes along, and it does a bit of work. It stops the medium. The low is obviously still paused. It now requests this resource, but it can't have it because the low priority task has locked it. So at which point the high priority one has to stop, which then means that the medium priority is allowed to continue because nothing else is happening. And at this point here, it's said to be, this is priority inversion because a medium priority task has taken priority over the high priority task. When the medium one finishes, the low priority can finish, it releases the lock, then the high priority continues. When the high priority finishes, then the low priority is allowed to finish. Now this happened, as I mentioned on the Mars Pathfinder thing, where what I believe kind of happened was they had some kind of low priority task that was something like grabbing meteorological data. And then a medium priority task that did set up the comm system or something. And then the high priority one was pulling the data and sending it up to be packaged off. And what happened was the low priority would start at boot time. And then the high priority thread would be suspended, right? It wouldn't happen. And then got some kind of watchdog process over the top that said, if this task doesn't do anything for a certain amount of time, there's something really wrong. So reboot. And then it would be back here again. And it would go through and it did exactly the same thing. So you just end up with this reboot cycle. And it's quite an interesting post there's a Microsoft blog somewhere that explains how they diagnosed it and how the hell you can fix something like that when it's many, many miles away. The third one, deadlock. This time, similar kind of model. Now we have 2 threads, 2 resources. I'm going to go quite quickly. Thread 1 requests a lock on resource 1. Carries on, all good. Thread 2 asks for one on resource 2. So now thread 1 has locked resource 1, thread 2 has locked resource 2. Now thread 1 requests for a lock on resource 2, which it can't have because thread 2's got it. Which is okay, because that'll just pause thread 1 and thread 2 will keep going. Hopefully at some point it'll release the lock. But no, it doesn't. It requests for a lock on resource 1. So now you've got a situation where both resources are locked and neither thread can do anything because they're both waiting for each other to finish, but neither of them will finish because the other one is still working, because they're waiting for the other one to release the lock. So, 3 problems that you will see quite regularly when you're working in concurrent programming. Now, the Apple's frameworks, and this isn't to say in any respect that Apple's frameworks remove these problems for you. They don't. They still exist, but it's important to keep those things in mind whenever you write anything concurrent. Apple has pretty much 2 frameworks for doing concurrent programming. One really low level called Grand Central Dispatch, GCD. It's known as libdispatch, or it has that nice logo if you're in marketing land because you need to market a concurrency framework. God knows what that was going on there. Or it has the operation queue paradigm, which is very similar but is much higher level. Both of them use this queuing paradigm. So rather than having a thread pool, rather than creating threads, rather than assigning work tasks to threads, you create a task and chuck it on a queue. And then something else somewhere will work out, well, how many threads do I need in my thread pool? Which thread should this piece of work go on? All of that stuff is taken away from you. And you do get some quite cool stuff for free. For example, there are bits of stuff in there that will help alleviate priority inversion. There's stuff in there that will help you with making things thread safe and all kinds of things. So how does this work? It's very simple. Each of these delightfully covered blocks represents a unit of work, and then the system, you add them to a queue in some sense, and then the system will just dish them out onto the number of threads that there are. So thread 1 will start working on one, then thread 2 will get the other one, and then they just work all the way through. Okay, so that's enough theory. I'm now going to attempt to do a little bit of live coding. Because I have absolutely no idea what time I need to finish, but this could be a hell of a lot longer, and I don't think we want more concurrency than we actually have to have. So I've cut out some bits and pieces. I'm going to talk about some bits, and then I'm going to show some bits of code as well. So we're going to start out by NSOperation. How many people have used NS, or if you, I don't really know what to call this anymore because it is NSOperation, but NS if you use Swift 3 is now gone. So I guess operation, which sounds now a bit weird, it's like that. Do you have that game where you have to take, you have like a body and it has holes in it and you have to take hearts, and we call that operation, so maybe that's it. How many people have used NSOperation in the past? Excellent, so I'm going to talk about it hardly at all. It's just a way of wrapping up a unit of work in some sense. Then you've got an object that represents that work being done. Now I've got some stuff here that I've built an image filter that I can do this stuff with. There are two ways to make a couple of ways to make an operation. The first one is to use a block operation subclass, which, is this big enough? It's probably tiny. Just tiny, isn't it? Let's get the large out. That better? Still tiny. Okay, if you can't see it, get some glasses. So the first one is to use a block operation. A block operation is a subclass of NSOperation, and all it is it takes a block or a closure, as we know it these days, and then that represents the unit of work. Now that's not particularly helpful because it's not overly reusable, but it's an easy way to generate to create one of these operations. And what I'm doing here is actually calling start on it, which again you probably would never do. But all I've done is wrap this tilt shift function, which is just an image filter, and it takes, oh no, not you. I don't want you either, I want you. Blimey, that's small. So I'll zoom in on that. So it takes an image and it applies this pseudo tilt shift thing. So tilt shift is where it makes it look like a model because it's blurry at the top and the bottom. I mean, my particular implementation of this isn't brilliant. Okay. But block operation isn't overly useful because, as I said, you can't really reuse it. You're just producing a block at any one time. So the alternative is to subclass operation to create your own operation. And then you've got this class which you can reuse however you want. So this has created a tilt shift operation. And you could reuse it with multiple images. Just create different instances for each image, and then you've got as many of these things as you want. I should mention all of this is available on GitHub, so that and I've written some notes in there, so in theory you can go ahead and read this in your own time if you so wish. Okay, but calling start on an operation is a bit weird. There's not much point to that, and I mentioned before queues, so each of those operations would be one of those coloured boxes in the queue that I have. And the way that you do that with NS or with operations is to use an operation queue. And this handles the scheduling of those particular tasks, those operations, across as many threads as you want, and it can handle it concurrently or in a serial fashion. And to do that, we've got exactly the same kind of operation. It's just a subclass of operation called tilt shift operation. I should mention that the way that you get these, the way that on these operations you actually implement your functionality is to override the main function. You create an operation queue. Just call it using the standard initializer is absolutely fine. And then here I wanted to, what's the word? Accentuate, I don't know, that's a terrible word. Point out, that'll do, that adding operations to a queue is really, really cheap. That when you add it to the queue, that's not when the work gets done. The work gets done at some other point in the future, we don't know when. So that's what this bit here does, and if I run this, I've got this duration function which just shows you how long something takes. So for here, the duration of adding all of these image filtering operations to the queue is about 0.7 seconds. But in actual fact, to filter those images, I know it takes a long time because I've made each of those operations sleep for a second so that I can actually see that it happens. The other thing you can do with the queue is decide. You're not allowed to decide how many threads it has, how many things it can run at once, but you can point out what's the maximum number of things that it can do at one time. And the reason for this is that Apple is abstracting away the actual details and the implementation of how many threads an app is allowed at any one time. And it does this for energy efficient reasons. So that if you've got an iPad and it's plugged in and it's got plenty of battery and it's, then it can have loads of threads. But if you've got an iPhone and it's got 20% battery left because it's 10 o'clock in the morning and the iPhone's 2 years old, then at that stage you want far fewer threads. You want to really power down the CPU. So that's what this allows you to do. You're not allowed to say, give me this many threads, but you can say, don't give me more than this. So here, if you choose 2, then it's much quicker than if I change it to 1, then it becomes a serial operation queue, i.e. it does one thing after another, and it's only allowed to do one thing at once. And you can see there that the... Sorry?
This is actually faster.
Yes, it is, isn't it? You're not supposed to look at that. It's getting faster. This is amazing. Why is that? Why is that? Well, that doesn't work, does it? Oh, I know why. Do I know why? Yes. This is why. Because that needs to go here. Brings up an interesting point. When do these operations start? They start as soon as you add them to the queue. So me changing the number of operations that can happen at once after I've added them is kind of irrelevant because most of them have already happened. There we go. So now if I go down, that's 1.6. And I really, really hope that if I change this to 1, then it will be slower. It seems slower, but that could mean anything. This is just a playground. Yes, it's 5 seconds. Right. There we go.
Managed to make it slow.
Not often you get a round of applause for that. Okay, so that's operation queues. Now, one thing that is, as I mentioned before, in order to create an operation, then you use subclass NSOperation, then you override the main function, and it is the main function that does the work. But that will not work if you have a function which is in itself asynchronous, i.e. it does you call it, it does the work, and it calls you back later on some kind of closure to say, I've finished. You can model those using operations as well. Unfortunately, it's a bit of a pain in the arse, and I don't really understand why it needs to be quite so complicated. But what I've got here is a subclass of operation called async operation. The reason that it is a little bit more complicated is because that you need to transition your operation through different states. An operation can be ready, it can be ready or executing or finished, right? So there are 3 states that it can be in. You have to transition it through those states in a KVO friendly fashion, which is why it becomes a bit of a pain, because you end up with all of this stuff where you're doing will change key for value and all that kind of stuff. But what this subclass that I've got here does is use a nice nested enum for to measure the state, and it just has a state property, so then you're using nice Swifty enums and that kind of stuff, and you're no longer having to do stuff where you're changing the underlying skanky Objective-C. So what does that actually look like when you come to use it? Well, I've got this image load operation which uses this simulate async network load image function, and it has a callback here that updates the image and changes the state. The important part with this subclass that I've got is that I must set the state when I'm finished, because then the state that I'm finished, then that fires off KVO, it tells the operation queue this operation is finished, so then it can go off and do the next operation. That there looks much neater once you've already built async operation. And I imagine that if you've ever done this, you've probably built something that looked quite like this, because that seems to me to be the same thing you always have to do. I don't understand why there isn't one pre-built, but I may just be being stupid. Okay, now I'm going to go on to something that's a little bit more interesting now, and in fact I think that means I've got might have some code to type in. Sorry, not type in, write. It's all very well splitting up your code into these nice little pieces of work that can go off and be done. But that's not particularly helpful, because actually once this piece of work is done, then I need to do another one. So the example I've got here, did I write it out at the top here? Yes, here it is. So I want to retrieve a source name from some kind of data store. So I'm talking about my image filtering application. And then once I've got that name, then I'm going to download that image, which is an asynchronous process. Then I'm going to decompress it using some kind of custom decompressor. Maybe I want to use WebP instead of JPEG or something like that. Then I want to apply a filter to that image. Then I want to apply a second filter. And then finally I want to display the image. That's like 6 separate little pieces of work. but they have to be done in order. You can't start applying the second filter to the image before you've downloaded the image from the network. So you need to be able to do these in order. And that's what the dependencies functionality within operations allows you to do. And the way you do that is you can add a dependency to an operation. So, excuse me, you can say that this operation depends on this previous operation. And then what the queue will do is it won't start the dependent operation until the dependency is finished. And at which point you can then go and find out, well, what was the result of that previous one? Now, unfortunately, it's not the nicest of APIs, because all you get when you add dependencies, that's all fine. It's quite a nice method to add a dependency from one operation to another. But then they manifest themselves just as an array of NS operations at runtime. So you have to go and find, well, what the hell operation was the one that was a dependency? So let's see. What I want to do first is down here, I've mentioned that you get this array of dependencies, and what you could do is search that array of dependencies for give me the previous an operation that is of this class. So then you're coding to concrete implementations, which, as we all know, you're not supposed to do that. So I think you can, in a far better way, using some fairly simple protocols. So for example, I'm going to make a protocol called filter data provider, and all this does is that it has an output image, because that's all I need for a filter, right, is an image, and we're going to get it. So that's all. So I now have a protocol, and all it says is that if I am an image filter, I need a data provider, and all that data provider needs is to have this output image property, so that then I can read that image in as my input. So now that I've done that, I can go into this tilt shift operation, and I'm going to implement the main functionality for this. So first of all, I'm going to try and find a image provider within my dependency list. I'm really glad that I chose great variable names. Dependency image provider. There we go. I can't type at all. Okay, so it could be in this dependencies array. So this is an array of operations. But I only want those ones where, oh no, I do need that bracket, where it is a filter data provider. Like that, right? So I can only read, as an image filter, I can only read in an image from something that is a filter data provider. Ah, thank you. Objective-C coming back to kill me. So I only want the first one of those because I'm lazy to work, and then I want to type that as well, filter data provider, thank you. Oh no, now I need another. And the input image equals none. So what I've done there, in the olden days I think you had to put where in there, but you don't have to put where in there anymore. Thank you. There we go. This is good, isn't it? I wish you guys were there when I was actually writing code. So what I've done here is I've looked through the dependency graph to find, have I got something that is a filter data provider where I can get my image? And I only actually want to do that if my input image value is currently none. I don't have an input image, so I'm going to grab one from my dependencies. And if that is the case, then I'm going to set my input image to this new thing here, dependency image provider. There we go. And then that's actually all I need to do there. Now I've set that in. What's wrong with that? What's wrong with you? Oh, no, I need to put the dot output image, right? Dot output image, there. And then the final thing that I need to do here is to extend the image load operation, which is the operation that I had before, to make sure that it is a filter data provider. And actually, I don't need to do anything else, because if we look back at the image load operation, it already has an output image property. So that's all I need to do. Now I can set the dependency chain, but before I want to do that, I want a word of warning. I'm going to use a custom operator. And normally I hate custom operators because it means that you end up with this thing where it's completely illegible and nobody knows what it means. In this particular instance, and I think this is what everybody who ever uses custom operators will argue, is that it makes perfect sense. And I think in this case, I genuinely think it will. In fact, let me write down what I would write beforehand and then I'll show you what it turns into. So I have to create a dependency chain. Now, what order do I want this dependency chain? I want the filter to add a dependency of the, what is it called? Image load? Image load. So that's the way that works, which isn't too bad, right? That says that, and I always have to think about this, which way round, which is the dependency of which. This says that the filter needs image load before it can finish. Now, if you then went on and built a chain of these, then this becomes a little less obvious, which is my argument. So I'm going to create a custom operator to make this a little bit easier. And the custom operator syntax has changed in Swift 3, which is a joy. And when I wrote this, then the only way to find that was to watch the, to read the, what's it called, Swift change thingy. So we now need to use this thing called precedence group. Now I'm going to call it chainable. And in here, I'm going to specify that, no, associativity is left. So is everybody aware of what custom operators are and what associativity means and what the order of associativity means? Okay, yeah? Anybody not and want me to explain it? Grand. Right, so I'm going to set the associativity left. That's just the way that they get bracketed together. This precedence group thing is new. That's the part that's changed. The other part that is, oh right, and then I need to specify that this is a custom operator and that it's an infix operator. So I'm going to stick an infix operator. And I'm going to make it look like this kind of thing because this is the operator everybody always uses for everything that they're doing. And that's the, oh, yes, chainable, there we go. And the other thing that's changed is that you can now put, in the past, if you wanted to put a custom operator in, then it was a global free function. Now you can put it as an extension of the type if you wish to, which I think makes sense here. So I'm going to extend operation with a static func, which uses this funny duck thing. It takes a left-hand side, which is an operation. It takes a right-hand side, which is an operation. And it will probably return an operation so that it's fluent. And then in there, we do right-hand side, add dependency left-hand side, and we return, I guess, the right-hand side? Yeah. So, oh, that's gone. So all I've done there is basically wrap up add dependency into this custom operator. In this precedence group, that's where you would also put the priority, but you no longer specify the priority in terms of numbers, but in terms of relationships with other precedence groups. The problem being, I believe, and I'm not far from an expert in this, that in the past, the precedence you would always specify in terms of an integer, and you'd end up with situations where if you have an integer and then an integer plus 1, and it turns out there's no integers between an integer and integer plus 1. So if you want something to go between, you can't. Whereas using this approach, then you can say, well, it's higher than this one and lower than this one, and then that'll put it in the middle. And then that becomes down here that I take my image load operation and I pipe the output from that into my filter, which to me is a little easier to understand, and it certainly is once you start having chaining loads of these together. And now if I run that, then, I mean, it's a fairly unexciting result because the output image looks exactly the same as the previous output images. All I've done there is, I mean, could we look through? No, I'm not going to look through. But you could, it loads an input. We specify the input image on the image load operation. That's all we have to do at the beginning. We add the dependencies. We add both of those operations to an operation queue. And then once we get to the end of that, then the output image on the final one will be the result. Okay, I'm going to, NSOperation in practice, this is just a bit of a demo of where this can go. And there's not a huge amount of code in here at all. It's not massively exciting, but basically, if you take a table view, then, I mean, this is the fairly standard vanilla example of this is why you need to use concurrency. And that's, if I take a table view, each of which has an image, each cell of which has an image in it, and to load that image, then I have to, in fact, we can see it here, I have to load the image, I then filter it, and then I output it. That there is demonstrating a bit of the chain in action. I've got this thing that's called an image provider, which has its own queue. So each cell will have an image provider, which has its own operation queue within it. It'll then go off and it'll load this. We populate this at, where do we do it? We do it here in the, I can't read what that function's called. Table view will display cell. So at the point that we're just about to display it, then we'll go and see if we need to, if we could got one of those image providers, and if we have, then we'll either wait for it to finish and then display the image. So the output operation is actually responsible for pushing that image onto the screen, and we pass that itself so that it knows how to do that. The other thing that's worth mentioning in this particular example here is this is new to iOS 10. This is the UI table view data source prefetching protocol. And that gives you two new methods. One of which is prefetch rows at index paths, and the other one is cancel prefetch rows at index paths. Now this allows you to preload any data that you will need to display before that cell is ready to be displayed on the screen. And it's as simple as that. You just get a list of index paths from the table view saying, at some point in the future, I reckon I'm going to need these cells. And then you can go off and start loading your data. You don't have access to the cell, so it's different from the traditional delegate methods, and it's different from the data source methods. All you have is the index path, but you can start those preloading operations. And that's what's nice about using NSOperation here, is that because I've built this image provider around that NSOperation queue, I can just start that going, and then later on I can come back and see, has this finished loading or not? If it has, then I can display it straight away. Otherwise, I rely on it to display that image once it's finished. And what that should mean is that, oh yeah, so there's now a new prefetch data source property on a table view as well to demonstrate this. So here's the table view. So those operations, they take a really long time to run. There we go, right. But when they do finish, then you see the images loading in. And what the data prefetching should give you is that, can we find where that data prefetching is? So the data prefetching stuff was not there, it's here. So you notice it's been called 13 times of loading different images, even though we're not very far down the table view. And in theory, as I start scrolling, then these images are already there, or most of them are anyway. In the past, then when you'd scroll, then they would kind of fade in as they loaded, like that bit there, right? But the prefetch means that they've already been loaded, which is cool. So, I mean, that's pretty quick through there. There's more stuff, like, feel free to take a look at that code, because it might be useful. So, from operations, which is the kind of high-level approach, I don't know what time I'm supposed to stop talking. I'll stop talking when you all leave, or when I've finished saying what I want to say. So. NSOperation, operations, operation queues. It's kind of the high-level approach, and I think it's got some quite cool stuff in there. They're being able to do dependencies, being able to make them cancelable, which up until recently wasn't possible with Grand Central Dispatch. It's got a fairly nice API. You can do some reasonable stuff with it. Maybe not the best, because it's quite old, but it's doing all right. However, that all sits on top of Grand Central Dispatch, libdispatch, which is the low-level C API, which up until recently in Swift had the most diabolical API to use because it looked like you were using C, because that's what you were. It's now far, far nicer. I'm not going to go into much detail because I'm sure you've all used GCD, and I'm sure that you've not just used it to wrap something on the main queue, because then it doesn't crash when you try and change which is what we all do. Well, what everybody starts by doing is, why isn't this UI updated? Well, I'll have a look on Stack Overflow, and it tells me that what I need to do is put this on the main queue. And that's everybody's introduction to GCD. I'm convinced it is. But you can do a lot more than that, obviously. As I said, the API looks much nicer. Now you've got these kind of pseudo objects. It's not, I mean, under the hood, this is exactly the same. It just uses, you can annotate your own C APIs, should you have them, so that they have really nice APIs within Swift. So you can do things here. It uses NS Swift name, I think. This actually calls exactly the same method, exactly the same function as before. But to us, it looks like it is an initializer, which is really cool. So I can create a queue. You can set quality of service on it. Getting the queue name, I don't know whether this has changed actually in the GM, but this was a bit of a pain in the arse because this didn't appear to have been annotated with the nice thing, so it's easy to get at. Instead it has double underscore. You can kind of get the queue name, but because of the way that dispatch queues work, there are actually only about 5 dispatch queues. When you create your dispatch queue, then it actually just gets filtered down into one of those 5 global queues. So asking what queue am I on doesn't really make any sense, because you're running on one of the 5 global queues. You're not running on the queue that you made. However, you can find out the name of the queue that you requested for it to be run on, which is what this does here, using this fairly hideous C string API, which is better than it used to be, but still not that nice. So you can get the queue name. So if I run that, we can see that I can find out the queue name that I'm running on, or I would be able to. There we go. So I'm running on the main thread when I run that there. Now, you can dispatch asynchronously and synchronously onto these queues. I should mention, sorry, at this point, we've now mentioned 2 types of queues. Operation queues, by default, are concurrent queues, i.e. you can run multiple things on them at once. Dispatch queues, by default, are serial queues, i.e. they run one thing at once. However, you can create either type of each. That doesn't make any sense. You can create concurrent versions of dispatch queues in the same way that you can create serial queues of operation queues. And within that, you can dispatch synchronously and asynchronously. If I dispatch synchronously, it means that I wait until that's finished. It'll happen on another queue, but my current thread will pause until that comes back. That's useful if you want to get a result from that piece of work. We'll see that useful later on. But be very, very wary of synchronous calls, because 2 synchronous calls can quite easily cause a deadlock. That's exactly the same thing. If 2 things are waiting on each other to finish, then that's a deadlock. I don't think we need to go into this. It's really easy to execute stuff on queues. That's about all I'll say. To create a concurrent dispatch queue, you use the dispatch queue initializer with a label, a quality of service. You don't have to have a quality of service, actually. And then attributes of a concurrent, which is worlds apart nicer than it used to be. Okay, GCD groups. How many people have used GCD groups? Okay, this is good. How many people have heard of GCD groups? Good, right. So I'll explain a little bit more about what they are, because I think these are some of the slightly more interesting things. If I've got multiple bits of work that are happening somewhere in Grand Central Dispatch, something that might be interesting to know is, when have they all finished? And what I don't necessarily want to do is have to put them all on the same queue, because if I put them on the same queue, I could work it out. If I put them on a serial queue, then I could work out when they finished, because I just put something on the end of that serial queue that says, this is the final one. But maybe I don't want them all on the same queue. Maybe I just want to chuck them all over the place, and I want to know, when is this lot finished? And you can do that with dispatch groups. That's really all they are. And in fact, actually all they are is a counter. You could implement this yourself fairly easily, because all it does is, when you do this thing, you enter a group and you leave a group. When you enter a group, it increments the count by 1. And when you leave a group, you decrement it by 1. So what that means is a group represents a load of bits of work happening. As you enter a group, then you increment that count, and then as each one finishes, you decrement it. And when you get back to 0, you can say everything in that group is done. There's a couple of ways you can use this. The first of all is that there is another method on a queue, so you can do queue.async, and then you can provide the group as well as the work that you want to do it. Otherwise, you can use manually, you can use group enter and group leave, which is equivalent to increment and decrement. And the example I've got to demonstrate this is something that I think arguably might be useful. And that is, I'm going to create a new version of the animate with duration method, which takes a dispatch group. Why would I want to do that? If I have 4 different animations running, and I want to know, have all of my animations finished? Then I could use this with a dispatch group to tell me all of the animations are done. And this demonstrates the fact that you can use dispatch groups and current asynchronous APIs, wrap current asynchronous APIs with dispatch groups to be able to get the functionality where it doesn't already exist. So how would I do that? So I've got this new method here called animate with duration, animations, group, completion. It's exactly the same as the method you all know and love, only now I've added this dispatch group parameter in there. And then all I have to do is, at the beginning, I do group.enter. That's me starting the work, so I'm saying I'm now entering this dispatch group, so I will do some work. Then I can call the animate, this one here, animate with duration, animations completion. So that's the method that we actually want to do the work, the same one that we used before. I just pass in all of the parameters that I've proxied. So my animations are animations, And my completion, I actually need a completion in this sense. So I'm going to get rid of this. And we'll put on here a success parameter. Oh, for goodness sake, learn the word. There we go. And then what we do first is we call the completion with the success. So that's, again, proxying that method. And then once we've done that, we can leave the group. We're saying that actually this work is all done now. Group.leave. Right, I don't need code completion. I'll do it myself. Thanks, Xcode. Right. That seems to have almost killed it. And then what I've got is several different animations going on at once. So I want to show, if I just have a quick look at those, we've got an animation that in its completion block runs another animation, and then completely separately I've got another animation running as well. So there's animations, one of them moves that square, another one rotates it, another one changes the background color. So if I run that, we've got to look at two different places. We're going to look over here for the animations, and then over here it'll tell you it's finished. And so that there was far, far easier to do. If you weren't using dispatch groups, you would end up nesting all kinds of different bits and pieces and trying to work out, has this completion handler been called, and all kinds of things. So dispatch groups make that really, really easy and really simple to use. Okay, next up, dispatch barriers. How many people, I think I might skip this out because I feel like I'm talking quite a lot and I want to talk about the thing at the end. Let me tell you what dispatch barriers are, why you might want to use them, then you can go and help yourself to the playground to learn about them. So I'll show you it in, I've got some slides for this, so I'll talk through them and then you can go and look at the code should you want to. So dispatch barriers, touch my theory. So we're talking about thread safety now. And the idea of this is I've got an object, I've got some memory, and I want to access it from multiple threads. And I actually want that to happen. Imagine then, I've got this memory here, it's got 4 ones in it. And it takes me 1 clock cycle to be able to change each of those numbers. So thread 1 comes along and reads 11111. And then thread 2 comes along and says it wants to write 22222. But that takes 4 clock cycles to do that. The first clock cycle, it changes the last digit, and then it will continue through. So then thread 1 reads now, it's got this 1122, which is completely inconsistent. That data makes no sense whatsoever. Then that starts writing 3333, and then down at the bottom we're now reading 1223. None of this is consistent. You shouldn't be allowed any of these numbers. And it's not right until the end when once both of these writing operations are finished, then we can read those values again. It's all about the consistency of the data. So the point is, if I read something, either it should be 1111 or 2222. It shouldn't be some weird mix of the pair of them. I want the data to be consistent. And that's an element of thread safety. And what dispatch barriers do to handle this is that you create loads of tasks on your queues, and they can all happen at the same time asynchronously on multiple dispatch queues. As soon as you create a barrier task, that means no other task is allowed to happen at this time. And you can use that to prevent any other stuff going on. So in the example I showed you there, all the reads can be simultaneous. They can be standard asynchronous calls to a concurrent queue. Absolutely fine. However, as soon as you come to writing, you don't want everybody else has to put down everything they're doing and sit back. It's like doing some kind of old school source control or editing a storyboard. Nobody else is allowed to do anything whilst this writing is going on. As soon as it's finished, you can read again. Now, I mentioned dispatch barriers, but there is another way that you can do exactly the same as this, and I'll mention it briefly. And that is, if you used a serial dispatch queue, that's one where only one thing can run at once. I don't have to do any of this. I put everything on a serial queue, and then you never can have a thread safe problem. As long as all of the memory write and read operations associated with this object happen on a serial queue, you'll never have any thread safety problems. However, if you're in a situation where you've got lots and lots of reads and not many writes, then dispatch barriers make a lot of sense, and they're really quite easy to do. If you want to look at those, then do feel free to go and take a look at that playground. So I want to finish up by taking a look at some alternatives to Apple, and hopefully I'll get a chance to implement one of these, a basic version of one of these, so that you can see that in actual fact they're not as complex as you might think they are. What I want to look at is promises, and these they've been around for many, many years, but they became popular in the JavaScript world not long ago. And in fact, in ECMAScript 6, which is like what modern people think of JavaScript as, they're part of the language, and they're really quite nice. And they come from having a problem like this, where if I had this kind of model that I had before, where I had a network request, a decompressor, an image resizer, a filter image, display image, each of those things relies on the previous thing finished. So if you have this model where you have a piece of input from the previous one and then a callback when it's finished, you end up with this kind of pyramid going across the screen where I can only start this operation, start this task once the previous one is finished, so I end up in that one's completion handler, and you just end up going across the screen. Which in JavaScript was a huge problem because everything is asynchronous, everything takes callback handlers, it's all terrible like this. So the idea of a promise is to split that out and say, actually, I don't know what the answer is, but at some point in the future, I will be able to give you an answer. And in JavaScript, that's all it is, really, but in Swift, we can go further and say, it will be an integer. I don't know when I'm going to have this for you, but at some point in the future I'll have an integer. And then I can treat this thing, this promise, this future, which is the same, another name for the same thing, I can treat this as if it were the value, because at some point in the future it will be. Now it'll either be an integer or it can be an error. And that's another key thing is, I showed you that pyramid where at each stage you took the result of the previous one and then put it into the next task and went round and ended up with this. If you add error handling in there, then quite often you would have, I would return two things. I'd return an error or I would return the result. And then you end up with error handling dotted in there. It's a real pain. Certainly is in JavaScript. So what does it mean with these promises then? So I start out with a string and I do some kind of function that returns to me a promise of an image. So this is like a file name and then loading the image. I can treat that image as if it were an actual image, because it will either give me an image or it will give me an error. Now if I've got an error, then I can just pass that to some kind of error handler. Now if I've got an image, then I can keep going. And I can now use a function on that image to return a promise of an image, which will then be an image or it will be an error. If it's an error, then we'll stick it to the error handler. The important thing here is I've only got one error handler. I haven't had to go through every single step of the process and put lots of error handlers in. The other point of this is that it changes the code, so it's no longer a pyramid, but instead it looks a bit like this. We have a network request that takes a URL, that returns a promise. Well then, once that's finished, then use the decompressor function. Once that one's done and we do the image resize, and we have this kind of then thing which takes these functions or takes these closures at each stage. And then finally we can have this catch thing, which is like the catch-all error handler right at the end. So I think I'm probably just going to show the code rather than stand here and type it out like an idiot. Because I can do that. I can't see what I'm doing because this is the smallest thing in the world. Right, if I check that out, then that'll be finished. I like that. You can just check out the end of the talk. Right, so futures, basically the same as promises. It's just a different name for the same thing as far as I'm concerned. If you're a functional person and have religious reasons why they might be different, then feel free to send me an email, direct to spam. Come on, scroll. I might have to, oh, here we go, there we go. Come on. So a future, right. So a future is the type that I'm going to create. It's going to be a struct, and it is generic over T. T is the result type. What will this thing return? I've got a couple of type aliases right at the beginning. I've got this concept of a future result handler. So this is a closure that will handle the result. So the result will be of type T. That's the thing that we're generic over. And then it will pass that. So that's just a closure that takes one of those things. That's how we handle the result. And then I'm taking, well, there's an async operation that takes one of these handlers and uses it. So that's how I will instantiate it, using one of these async operations. Notice this is something new in Swift 3, is there's a lot of dotting around of escaping. This is, if you've not yet seen Swift 3, this is a change in the default behavior. In the past, everything used to be escaping by default. Now everything is no escape by default. So be prepared to dot escaping around the place. And you can understand. It does make sense, but I was mildly irritated that I had to learn what it meant in order to be able to put it in there. Okay, so how do I initialize one of these features? Well, I give it an asynchronous operation. That's all I'm doing, is I'm wrapping these async operations. And what I'm going to do with that is I'm going to keep it. And that there is precisely why I have to put escaping, is because I'm keeping hold of this closure. That's basically what escaping means. It's just helping the compiler. Now I have two methods on this feature. I should point out, sorry, I should have prefaced all of this with, this is an incredibly simplistic implementation of this. There are proper implementations. I'm just trying to demonstrate that these aren't complicated things. Because if you were to take a look at some of the implementations, you might think, this is mega crazy complex, I don't understand it. It's not that complicated. So, what would you do? So there's a resolve one. That means that I've got this future, tell me what the answer is. Resolve this from being a future to an actual value. All that does is it takes a future result handler, so that's the thing that takes the result, and then it calls the async operation passing in that handler. So that means it will evaluate that asynchronous thing that you instantiated it with, and then use the result handler to pass you back the result. And then the other one that we need is then. Remember we had then to chain them together? This is mildly complex, but it's only because of the syntax, really. So then will be generic on another type U, and this is so what then does is it takes a closure, an asynchronous function, that takes type T, that's the result that you get from using the future that we've created, and it will turn that into type U, which is what we're generic over here. So all that does is it creates another future over type U, and then it passes all of those bits and pieces in, so that then we've now got another future that's wrapped up the existing future. It's not that complicated. It looks complicated, but it isn't. So how do I use it? Well, if we have a look down here, then this is, so I've created some random things here that don't do very much, but they demonstrate it. These are just asynchronous functions. This is what it looks like if you don't use futures. We have that kind of thing going across the page, making a bit of a mess, and then right somewhere in here is where the output comes. Now if I change that for using the futures, then I end up with this kind of approach where I instantiate it with each of those functions and just using the then thing, and then finally have resolve on the end and where I print out the results. Now if I run that, then we'll be able to see what it looks like. So down here, I've helpfully printed out the same data in two different ways to make it even more difficult to tell that it's the same thing. But honestly, this here is this array. So this bottom array is done using futures. This array is doing, it is the same thing, right? It's the same thing, only we get a much nicer syntax for being able to produce it. At this point, I'll point out that do not go and use this implementation of futures. This is not an implementation of futures. This is a demonstration of a toy example of how you can build futures. In a more proper implementation, you would be using something like this. So you'd have the enum that we saw earlier today with the result, where you would be over the result type, and you'd also be able to pass back an error. It would then have a success case and a failure case. You could use that inside futures, which then means that you can have that catch thing right at the end. So all you do at each in your then function is you switch on the case of the result. If it's a success, then we do what we've done. If it's an error, we just pass that error down and we can catch it right at the end. Now there are some really great implementations of this kind of stuff. There's something called, I've forgotten, bear with me a minute. Does it say it here? No.
Bright Futures?
Bright Futures is a Swift implementation, and there's something called Promise Kit, which is an Objective-C version, which also works perfectly well in Swift. Future Kit as well, okay. Okay, so the last kind of thing that I want to finish up with then is to imagine even, that this promise pipeline accepted a sequence of values. At the moment, this promise pipeline, we just put one value in at the beginning, and we get a promise at the end, or a value at the end, or an error at the end. But imagine instead that I could keep pushing values into this promise pipeline. That, he hand waves, is pretty much reactive programming. So if you've heard about Reactive Cocoa, RX Swift, or any of the RX family, RX Java, or any of the RX extensions, that kind of stuff, it's basically the same, pretty much, right? You build up a pipeline of things that can happen in some kind of asynchronous way somewhere else, handled all of that stuff for you, The result of this operation then gets fed into this one. I can pump loads of stuff in there, and then out the end of it, I will do some stuff with it at the end. That's basically, or the alternative way of saying it is that promises or futures are a specialized case of reactive programming. And with that, I'm going to pretty much leave it, because that might be a little bit controversial. I don't really know. So in conclusion, concurrency is hard. You will screw up. It is hard. We all screw up. It's really difficult to point out things. I should mention, actually, that although it is hard and you will get it wrong, check out the thread sanitizer, which is new in Xcode 8, because that is pretty good at being able to spot the thread-safe issues. In fact, it's really good at spotting thread-safe issues. It's good at spotting... what else does it do? I know it's the memory debugger. It does a few other things as well, but do check it out because it's quite cool and you can spot these things using that. I should mention at this stage I forgot to introduce myself at the beginning, so I'll post-introduce myself. My name's Sam. Hello, thank you very much for coming. I hope you enjoy the talk. I work for a company called Raysware, which is the company behind RayWenderlich.com. Ray would like it very much if you were to go and look at our website. That's a new website that I've been spending a long time building. This talk was kind of a very brief intro to a video series that I did on there called Concurrency, so you can check that out. The code is available at this particularly easy to read URL, because I don't know whether that's a 0 or an O, and I typed it in. I'm on Twitter, and if you want any, I have some like discount cards, and if you want to deface Johnny's creation and stick a RayWenderlich.com logo on the back of your laptop, in your own hands be it, but do help yourself to it. Thank you ever so much for watching this late in the day. Cheers.
Thank you very much. All right. I'm sure we have no questions. No, I'm kidding. I'm sure we have some. Is everybody still here? Like your brains stayed in the building? All right. Questions? Anyone? Come on, go ahead. Because otherwise, I'm going to have to figure out a question about concurrency.
That's all right, I don't mind. I can
mind.
make up some questions if you like. How do you come looking so attractive?
There's a question.
Well, it takes many hours.
Are UIKit or foundation classes per default thread safe or per default?
Sorry, pardon?
It's me.
UIKit and foundation classes and functions, are they thread safe by default?
Generally no, I think is fairly safe to say. They will make quite a big deal out of it if it is thread safe. The majority of stuff really isn't thread safe. So anything in UIKit should be only accessed from the main queue, main thread. I think that's a good rule for life. I don't know, that's a bit of a rubbish thing. As a general rule, things aren't thread safe. They will point things out if they are thread safe. And off the top of my head, I can't think of a whole lot that is. There might be some bits and pieces in core data that are thread safe, I think. But as a general rule, no. Okay. But they will point out to you very explicitly that stuff is thread safe.
Stuff is thread safe. I'm thread safe. It's all fine. So pass the mic if somewhere there's another question. Do we have another question? Otherwise, I'm sure you are staying tonight.
Oh yes, I'll be around.
So you will probably follow at Mühlenkirch, and then you can ask a question about concurrency after a couple of beers.
I get much better at answering questions about concurrency after a couple of beers.
That one's going to be very funny. All right, thanks, Sam. That's awesome. I just have a couple of words, but give him a round of applause, a big one. As you can see, my computer hasn't been backed up for a while. I didn't even know where my pointer is. If anybody sees my pointer, just let me know. That's interesting. Oh, I found it. So I just want to finish very quickly with what the heck? Okay. So there's one thing I not totally wanted to do because. Well, two things. Thanks again to 7P. And if at one point you want in the future to help us run this conference with a bunch of cash, the logo of your company can be there. It doesn't have to be that it's only 7P sponsoring this thing. Speaking about 7P, I would like to have my colleague Ollie to come here on stage with me, because you wasn't there when I said thank you to you. You probably have seen the guy walking around for 2 days like crazy. So, he actually has an actual job. He's a designer. He's like design.
Yeah, but it's just design, so it's not really an actual job.
Yeah, he spent his time in Photoshop. And it is actually, I'm sure it's going to change at one point. It is the last guy in the whole team, in the universe of our team, to not have a Mac. But things will change. Yeah. So whenever we need to change our password in the IT system here, we run to SPC. So thank you. You did an amazing job. And yeah, now I'm just going to do something that I do normally at the very end, which is always like, say thank to some people. Obviously, I want to say thanks to everybody, but I always do this running number of the companies who were buying the most tickets, and most of you bought one ticket, a couple bought 2 tickets, and then we had one company who bought 3 tickets. So thanks to StudiTemps, thanks to them. I was speaking to you to them. Where are you guys? Somewhere, or they left already. They left already. That happens when it's the last talk. But it's interesting because they were actually Ruby on Rails developers, and they have not so much clue about Swift yet, but they want to look into it. So they are server-side guys. And then all the way from Croatia, I want to say guys to Mašinerija. Did I get this right? Did I pronounce this right? No, wrong. Whatever. Thank guys, they bought 4 tickets, so it's great. I'm happy to see you again next year, and the next time I'm in Zagreb, I will let you know. And then, thanks to Rewe Digital. So this is a funny one. Stefan actually wrote me an email when we had 5 tickets left before to be sold out. And he wrote me an email, said, we need 6. And I was like, I think we can do something. And, and we did something, but then we were sold out. Not quite though. So first, one thing I want to say thanks to a couple of people. Those are the 3 first who jumped on the ticket. So Franck Lefebvre, it's always the first one buying. And then Tim, are you still here? Tim. Yeah, you're still there. And then Michael, which was a speaker last year, actually bought a ticket. And always believe in your dreams. Those 2 guys actually got a ticket yesterday. Are you still in the room? Yeah. So because they were on the waiting list. So because some people had to cancel, always believe that the waiting list there's a reason why it's called a waiting list. And that's pretty much it for now. I will say see you in 2017. But obviously I had to put it in a very special way. And that special way is that in 2017, I have something very important to tell you. We will get rid of the square brackets. That's it. Thanks.